Now let's talk about logic gates. So we use logic gates to perform functions, inversion, which we'll also call the NOT function, and or NAND, NOR, etc. We'll talk about these functions. We can have single input gates, which are the two types of gates are NOT gates and buffers, or two input gates, or multiple input gates, which are versions of those two input gates. These are the simplest gates we can talk about, the NOT gate and the buffer. It's also called an inverter. And so an inverter takes an input, in this case A, and feeds it to the output, but it inverts it before doing so. So if the input is A is 0, we get an output of 1. If the input is 1, it inverts it, and we get an output of 0. And so these gates have a name, symbol, equation. So this is the way we write y equals a bar. So we pronounce this as y equals a bar. We don't say y equals bar a. We say y equals a bar. And we also have what's called a truth table. And this gives the function for every possible input combination. And so for a single input, well, possible inputs are just 2, right? 0 or 1. And so we have our truth table function here, giving the function. And for the buffer, we have a similar thing, except for it just outputs whatever is input. So if we feed in a 0, we get out a 0 on y. If we feed in a 1, we get out a 1 on a y. And so the equation then is just y equals a. And you'll notice a difference between the buffer and the inverter, or the NOT gate, is this little bubble. And this bubble at the end of the gate indicates inversion. So it's taking the input and inverting it before it sends it to the output. We can also have two input logic gates. Here's our AND gate and our OR gate. We have, again, our name of the gate, the AND gate, symbol, has a flat line here and a curved line on the output. Equation, y equals a and b. We could write that as y equals a. This is the AND symbol, but just like in multiplication, we've overloaded that multiplication symbol. It's simpler to write without the AND symbol in there, and so we can basically use shorthand for that and just write y equals a b and take out that AND symbol in between there. But you can use it, just makes it fewer symbols on our page. So y equals a and b, the AND function is true when both inputs are true and false otherwise. So it's like, just like we use in everyday life, you can go to the movies if you have $10 and you can get a ride there, right? So both of those cases have to be true in order for you to watch a movie. So same thing with the AND gate. If both of the inputs are true here, A and B are both 1 or true, then we get a 1. Otherwise, we have zeros. The OR gate is also like we use in everyday life. You can go to the movies if you, if you have $10 or if your friend gives you a ticket, right? Either way, you can go to the movies. And so the OR gate, our symbol has this kind of curved front and then more pointy end here. And we overload the plus symbol, but this means OR. A or B, and there's no shortcut for that. But we pronounce this y equals A or B. And so this output is true. Y is going to be true if any of the inputs are true. Right? So here we have B being true, so that makes the output true. Here we have A being true, that makes the output true. And here we have both of them being true. And so the only case that this is not true is in that top case where neither of the inputs is true or 1. In every other case, the output is 1. So here are some other 2-input logic gates. We have the XOR gate. This is not pronounced XOR. It's pronounced XOR. We have the NAND gate, the NOR gate, and the XNOR gate. So the XOR gate is called an exclusive OR. That's what the X stands for. It's exclusive OR because it acts like an OR gate, has a similar body, but it has this extra line in front of it. And it has the kind of the OR symbol here, but a circle around it to indicate exclusive OR. So Y equals A XOR B, because the outputs can be true if A or B is 1, kind of like the OR gate. So A or B is 1, but not both. So the XOR gate differs from the OR gate in this place. So when both inputs are true, exclusive OR outputs as 0. Okay, so exclusive OR differs from OR in that exclusively one of the inputs can be 1 to make the output 1. So here we have B being 1 but not A, and A being 1 but not B. So our NAND gate and our NOR gate are similar to the AND and OR gate, except they invert the output. So you can see that bubble on the output indicating inversion. And we have Y equals A and B, all of that bar. Okay, so it inverts. Remember that bar means inversion and the bubble means inversion. And so we get inversion of the AND gate. So N stands for not and. So NAND stands for not and. So the AND gate would have been a 1 here, right? If we had an AND gate. So the NAND gate's the opposite of that. Instead of a 0, we get a 1, 1, 1, and then a 0. So our truth table for the NAND gate is the opposite of what it was for the AND gate. That's the inversion of that. NOR gate stands for not or. So N means not or. And so here we see the bubble and we have our OR function, but now we have this bar over it. So NOR is a not OR gate. With an OR gate, we would have had 0, 1, 1, 1, right? It would have been true whenever any of the inputs are true. The output would have been true whenever any of the inputs are true. Not OR is the opposite of that, so we get a 1 here, right? Or we would have gotten a 0 there. So not or NOR will get 1, 0, 0, 0, the opposite of what we would have gotten for an OR gate because of this bubble and this bar, or this bar indicating inversion. XNOR is not XOR. And it was too hard to say XOR, not XOR. It was too hard to say XOR, and so we put the N here. Right, so this is the XNOR gate is the inverse of the XOR gate. So here we see our XOR gate, but we now have this bubble at the end. So we have our XOR function here with a bar over it. And so XOR would have been 0, 1, 1, 0. That would have been XOR. But now we want the inverse of that, not XOR or XNOR. we get a 1, 0, 0, 1. There's our truth table for our XNOR gate. And you'll notice that for a 2-input value, A and B, when A and B are equal, so when A and B are both 0, for example, we get an output of 1. Or when they're both 1, we get an output of 1. So when they're the same, either both 0 or both 1, we get an output of 1. So XNOR is also called the equality gate because it outputs a 1 when the 2 inputs are equal or the same. So we can also have multiple input logic gates, and they work similarly to the 2-input versions. So here's our 3-input NOR gate, or NOR 3. So now we just have 3 inputs to our NOR gate, but the symbol looks, the same. And now our equation is A or B or C, all of that bar. And note that the truth table rows are listed in binary order. So really we could have listed in any order, but regularity is going to have us listed in binary counting order. So we have 0, 1, 2, 3, 4, 5, 6, 7. Okay. And I often in truth tables put a line between each group of 4 just to keep alignment. It's easy to lose alignment when you get more rows. So for the 3-input NOR gate, well, we're going to have a 1 here, right? Or this is a not or it would have been 0 and then 1s everywhere else, right? When any of the inputs are 1, they would be 1. And so the 3-input NOR gate is going to be the exact opposite of that. Right? So we have a 3-input NOR gate. This would have been an OR 3, a 3-input OR gate. Not OR 3 or NOR 3 is the opposite of that. And so here we have our truth table for that. And 3, well, similar to a 2-input AND gate, right now we have 3 conditions in order to make the output Y true. They all have to be true, right? You have to have a $10 and a ride to the movie and permission from your parents. You have to have 3 things to be true in order for you to go to the movies. So the only case that a 3-input AND gate would be true is in the last case where all of the inputs are true. And then we're going to get zeros everywhere else. So XOR is an interesting one. So let's look at a 3-input XOR gate. So 3-input XOR gate, A, B, and C, and Y, the equation is still going to be similar, A XOR B XOR C. And here we have our truth table, A, B, C, and Y. Again, this is written in counting order, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And then I like to put that line between every group of 4 to keep alignment. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And so 3-input or multiple input XOR gates, the output is true when an odd number of inputs is true. So when we have, here's an odd number of inputs, so only C is true. We just have 1. Here we only have B is true. So that's true there. Here we have an even number of inputs. So B and C are both true. So it's not, that one does not have an output of 1. Here we have an odd number of inputs, being 1. And not odd, not odd, odd. And so our 3-input XOR gate has, or 4-input or 5-input, or actually our single input XOR gate follows this rule as well. It's called odd parity, where the output is true when an odd number of inputs is true. If an odd number of inputs is true.